And anybody need a handout from last time? So welcome to lecture 4. If I got it right, evidently I had it right on wrong on Monday. Dairy Club will be doing some work time, 6 o'clock up at the dairy, moving and cleaning stuff that we need for the sale on Thursday, and then painting, if I heard your president right, after 4 o'clock on Friday. So if you have an opportunity to join, it could be a lot of fun. If you have some artistic talents, it would be very helpful if you showed up. We can also generate, if you want to bake some things that are new, we can generate some new cutouts. We do have some plywood that we can recycle and do some different things if you feel like it. Want to make some cows, some cutouts, whatever strikes your fancy. Lab this week, everybody have a ride up to the dairy. So bring your laptops. We're going to be working with the feeds that you sampled last week. We'll probably start our feed ID. So you're going to be introducing feeds, the forages this week. We're going to be running dry matters 3 different ways. So we'll be meeting in the other classroom to do that. In between running those dry matters, we'll do some fun with the carbon cycle, and we will talk about feed preservation. What do we have to do to get that done? So should fill up that 2 hours. Question from the class: does the dairy test the water? Campus and the dairy, I believe, test water twice a year. As a public institution, and we have our own wells here, we kind of have to do that by law. So not anything usually comes back that's kind of out of the ordinary, but we do test it twice a year. So last time we talked about dividing feeds up, and what we're getting at here are the nutrients. So dividing the feed up into nutrients, the first thing we pull out is the water. So the water, and we separate that from the dry matter, which contains the other 5 nutrients. We take a feed that we haven't touched yet, is sitting there. We call that as fed, as we would present that to a cow. So analyzing our feed, we've collected our sample. We know how to do that properly now. We're going to, once it gets to the lab, they're going to prep it. So they're going to dry it down. Usually they'll take a subsample of whatever we've delivered. They'll go through a quartering method similar to what we did. At least that's what we did in the lab I worked in. And then we grind, after the sample is dry, we grind that down to get more accurate sample measurements. So we go from the prep step to the measurement step. And if you're doing wet chemistry, and we'll talk about the difference, you're going to do one measurement at a time, one assay at a time. You'll do crude protein, you'll do fibers, you'll do fats. you'll do minerals, you'll do them all separately. If you're doing an NIR, a scan can, at least in theory, let you know where everything is all at once. So, but as a rule, we measure one thing at a time. We take the amount of feed we put into the sample, we take the results we have, and we start to calculate the percentages. How much protein is there? What's the percent NDF? What's the percent fat? So collecting that information, and then they'll report those results. When we're analyzing feed, there's going to be two methods that we can deal with. One is called wet chemistry. That's the one that's been around for hundreds of years. And then near infrared reflectance, we're starting to get a good feel for that. And it's become more and more popular given the costs associated with that. So if you're doing a full wet chemistry sample, you're probably looking at $100 these days. And you're talking about 4 or 5 days to get the results back. With the near infrared, you can get your results back in maybe 2-3 days. And you're usually looking at least to get started, maybe $20 to start. So what are the advantages and disadvantages? Why would you pay more for wet chemistry and wait a little longer? Or why would you pick the near infrared method? So let's talk about the wet chemistry first. We're looking here at an actual chemical process. Usually there's a liquid involved. Usually there's reagents of some sort, acids, detergents, catalysts, all that stuff. You take the feed sample, you put it in some sort of container, usually a glass beaker or flask. You add the chemicals and solutions that you need to, and then you measure what happens. How much disappears from or goes into the solution, how much remains as a solid is usually one way of doing that. For proteins, you measure the amount of ammonia, amount of nitrogen that's liberated from the sample using the chemical processes that are said there. So pluses of this, very standardized. So we have national standardization, chemists all prescribed recipes, steps that happen, and we're looking at something that's extremely reliable. If you get that measurement, you can be pretty confident that that is in fact what that measurement is. Negatives, they tend to take a lot of time. To get a good NDF takes 3 days. So you got to figure out the dry matter on that sample. You run the sample, you got to dry it overnight. You weigh it the next day, then you ash it. You put that ash in a drying oven, then you weigh the ash remainder. So you're looking at 3 days to get that sequential process down. If you add ADF and lignin to that NDF, you're looking at a week to get that sample done. Money, you're dealing with more reagents. So variable cost to run each sample, there's a lot more money tied up in the variable cost, the acids, the bases, the reagents, and you need skilled labor to run these samples. Somebody that's practiced is able to repeat these things with speed and accuracy. So all those things tend to slow your results. We compare that to the near infrared. You're going to send a beam through a sample. So once the sample is ground, it's put into a disc that's got a clear panel on each side. And you're going to force that beam through that. And you're going to measure the pattern generated by that particular feedstuff. So certain chemical bonds, the carbon-carbon bonds have a different pattern than the carbon-nitrogen bonds, the carbon-oxygen bonds. You need a carbon bond there to measure it. You can't directly measure water, you can only infer. You don't have a hydrogen-oxygen measurement. So you compare the pattern generated to a reference set. So if you have a whole lot of measurements associated with corn grain, And when we get this pattern, that means it's 10% protein. We get this pattern, it's 20% protein. And we see which of this unknown pattern or generated by the unknown fits a previous sample best. And then that's where we conclude that that's the measurement we're getting. So pluses, very fast. So once you get the sample dried down, you pop it in the disc, you got almost immediate results. Cheap on a relative basis, the variable cost, those discs are recycled. So it's relatively cheap. You don't have all the chemicals, you don't have all the time, you don't have the repeated drying and ashing steps over and over. The machine itself costs a lot to get started. So you got a lot of upfront costs, but once you have those, you can go very quickly and very cheaply. So after the startup costs, negatives, it's only as good as its reference set. Now, we've been doing this for 15, 20 years now. We're starting to get more robust reference sets that every possible option or pattern out there has been seen on some level. As we mentioned, you need those chemical bonds. You can't measure minerals in NIR because the minerals are free, they're ions loose, they don't have a chemical bond to anything. The NIR will give you mineral results, but they're just a correlation. They're not at all accurate. So don't even look at the NIR minerals. And you need a relatively clean sample. It does best with homogeneous samples. It's all corn silage. It's all alfalfa. It's all grass. When we start to mix things together and we don't know the proportions, well, how much grass is in the sample versus alfalfa, we start to get a little shaky. Again, we're only as good as our reference samples. TMRs, I probably wouldn't do them with NIR. I'd probably run wet chemistry on those, especially depending on what you're looking for, which is another story. So there are advantages and disadvantages. If you've got a straight forage in New York, the reference sets are pretty good. You're close enough. You're within the sampling error of what it actually is. Versus grains, they've been doing them for years now, and those sets, pure grains, are very robust. So any questions on the methods of analyzing? We'll be speaking generically about those as we go through the different nutrients. So pull out your letters, see what we remember from last time. What likely increases water intake? A, eating less feed per day, eating more salt per day, producing less milk per day, or eating wetter feed. So what would we surmise leads to increased water intake? So B is what we're looking for. Where doesn't our animals get their water from? In this case, we'll talk about a cow. Does she get it by drinking it? Does she get it by eating it? Does she get it by metabolism or respiration of the body? Or does she get it from the new remodeled Dollar General downtown? So the first three are our sources of water. We need to remember those. So let's talk about carbohydrates. This is the first fraction in the dry matter we'll deal with. Does anybody know anything about carbohydrates? Energy. Most of the carbohydrates are burned, respired to release energy. It's the bulk of what we will consume. So back in the old days, they used to talk about you'll get all your nutrition from a single pill. Well, you can probably do all the minerals and vitamins and maybe the protein and all. Fairly tough to swallow pill, but you can never get all the energy from something this small. You're going to need more volume to get the energy that you need. So we're thinking about carbohydrates. We're looking at the chemical formula of C representing carbon, hydrogen 2 times, H, O. So if you look at that, we look at carbon's hydrated, H2O is water. So when they first figured the relationship out, that you've got a 1 to 2 to 1 ratio, they came up with the name carbon's hydrated. They weren't really sure that, or didn't know that that's not really how they're arranged, but the ratio of those atoms holds more or less for carbohydrates. So it's not a perfect relationship depending on whether hydrogens have been donated or there's a carboxylic acid group in it and stuff like that, but it's close. We break up our carbohydrates based on size. The first thing we'll talk about is the monosaccharides. They are the single sugar molecules. So we're going to talk about things that you may have heard before. You've heard of glucose probably. You might have heard of fructose. You might have heard of galactose if you've studied for the dairy quiz bowls. Those are all single sugars. And then what happens with carbohydrates is how big a chain of those single monosaccharides, those monomers, do we run together? So this is glucose molecule. It can come in a chain form. Glucose has 6 carbon atoms associated with it. Or it can take the N carbon, numbers 5 here, 1 and 5 will form a bond. So you've got 1, 2, 3, 4, 5 carbons in that ring and 1 sticking off it. Most of what you'll see in nature is the ring form, and that's fairly stable. We can take 2 monosaccharides, stick them together, and we form disaccharides, di for 2. Anybody know what sucrose is? That's table sugar. It's made of a glucose and a fructose. Stick them together, you get sucrose. That's table sugar. You get it from sugar beets. You get it from sugar cane. Down south, lactose. Everybody knows where we find lactose? What's lactose? Milk sugar. So we stick a glucose and a galactose together. That's going to form lactose. Maltose is 2 glucoses stuck together. So we take that glucose and fructose, we stick them together, we get sucrose. We take the glucose and the galactose, put them together, we get lactose. The last group we'll talk about in this class is the polysaccharides. So something more than 2 stuck together. Polysaccharides we'll refer to in this class, certainly starch. That's a part of our plants. So that's a way for the plant to store glucose until it needs it. It's making all this glucose from photosynthesis. We're going to string them together, long branch strings. They're going to be starch. If an animal has excess glucose in their body, they can form glycogen. Same sort of shape, different source. So you have starch is from plants, glycogen is from animals. That glycogen will be in the liver, stored for later use. Or, has anybody heard of carb loading? Anybody carb loaded for an athletic event? Lots of starch the night before. The idea behind that is to form glycogen in your muscles. So you have that glucose in your muscles ready to go. So you've got that quick burst of energy. Everything's loaded up, prepped, and ready to go, like filling up your gas tank. Starch and glycogen are available to animals. If you or I digest either starch or glycogen, our bonds, our stomach acids can break those apart. Enzymes in the small intestine. The next group is the cell wall components. Hemicellulose, cellulose. In this class, we'll throw lignin in there, although lignin really isn't a carbohydrate, but they're all kind of mixed together. Those polysaccharides form the cell wall of plant cells, and animals cannot break that connection between our individual glucoses apart. We need the help of bacteria to get that done. So what are we looking here? Starch and glycogen. Well, starch in this representation of a plant cell, the starch is going to be inside the cell. The hemicellulose, cellulose, and lignin is going to be in this outer green area, the outside, the surrounding, the shell that holds the plant cell. So we're thinking about two different locations and two different purposes for those polysaccharides. When we take a plant cell, it would be helpful to sort the cell contents, which our digestive tract handles differently, from the cell wall, which our bodies will handle differently. To digest cell contents, focusing on carbohydrates at the moment, different processes than digesting, more accurately fermenting the cell wall. So if we could divide our plant cell to know how much cell wall is there, which is mostly carbohydrates, and how much cell contents there is, which is a whole lot of different very digestible, readily available things, doing those two piles would be helpful. So if we're thinking about cell contents, we've got the sugars and starches. Those are carbohydrates. The proteins will usually be there, the fats. We think of the cell contents as readily fermentable, readily digestible, readily available sources for build and burn to the animal. Cell wall is not digestible by mammals. We need help. So the cow has the rumen full of microbes that do the work unlocking those. Cell wall must be fermented to unlock those carbon units for the animal. Our mammalian enzymes are not going to take care of it. So we're thinking about a cow, we're going to need good rumen function to get those complex carbohydrates, that cell wall, digested and available to the cow. So we've got the outside cell wall, nutritionally different from what's inside. If we look closer at the cell wall, you've got patterns there, you've got a net, a web of the different components. So these yellow tubes here are the cellulose molecules. Each of these individual dots might represent one glucose molecule. You've got plasma membrane. Does anybody know what those are made out of? Anybody remember from biology somewhere along the way? What is a cell membrane made of? Phospholipid bilayer, ring a bell for anybody? So those are phospholipids that self-organize and form the cell membrane. We're focusing on that plant cell wall. So you're going to have hemicellulose, these little tan chains that are going to act as glue or nails, holding that cellulose in place. You're also going to have pectin in there doing the same sort of thing, kind of holding that cellulose in place. You're not seeing the lignin so much in there. So the bulk of cell wall is cellulose, but we do have other compounds in there. And those are not as readily available to the cow as some of the others. Here's another cartoon representing the same sort of thing. In this case, our blue tubes are the cellulose. We have the cellulose and pectin kind of acting as glue or cement, nails holding those things in place. We know as the cell grows, they're a little bit loose. As that cell gets mature and full size, that pectin and cellulose come in and hold things definitively in place. So you've got the cell, generically speaking, the plasma membranes on the outside, and then we work our way up from the center of the cell in both of these diagrams. So how do we measure that? And we use the detergent system. I think you still have that slide. So the detergent system, put together by Van Soest. It's probably animal science's version of Einstein. This analysis came in the 1960s, and he saw that there were problems with the crude fiber method. We'll talk about that a little bit later in class or lab, but the standard now is the detergent system. So the idea with the detergent system, whatever part we're dealing with, there's 3 different types of the analyses we'll talk about in this class. We dry the sample out, weigh out that, dry it, grind it. Then we take that ground dry sample, we weigh it out, usually into a beaker. We add a solution to it and we boil that sample for an hour. Then we filter and dry, see what's left. And we weigh the residue and figure out how much disappeared. What left on the filter paper in the Gooch crucible, which is a filter crucible, means something, and what disappears means something. So what we're trying to do with the detergent system is to separate the soluble components in a various reagents to the insoluble or from the insoluble components. What's soluble, what's insoluble in different reagents has biological meaning. And that's what the beauty of this system is. So we'll start with the neutral detergent as the reagent. We take the sample, we put it in the beaker, we put in a detergent solution that is set to pH 7. Everybody know that pH 7 is neutral pH. So you go to great pains to make sure you'll correct that to make sure you're at 7. You'll boil that for an hour. So you sit there, you watch, you wait till it comes to a boil, then you set the timer, and 1 hour later you take it off, filter it, see what remains soluble and insoluble. So what we're thinking about with neutral detergent is we separate the cell contents from the cell wall. So in the case of neutral detergent, the cell contents, the protein, starch, sugars, DNA, is all going to go into that detergent solution, and it's all going to pass through the filter. And what you're going to be left with is what's called neutral detergent fiber, the cell wall. And that's going to be made up of hemicellulose, cellulose and lignin. And some, no, not pectin in the NDF, but so you've got that there. So neutral detergent fiber, we'll call that NDF. And how I remember what's in neutral detergent fiber, I look at my first letters, HCl. I don't know why this works for me, but it does. HCl, hydrochloric acid, hemicellulose, cellulose, and lignin. Cellulose is the most abundant. You have some hemicellulose, and then you got a little lignin. But those are all part of that cell wall component. Another solution we might consider is acid detergent. We're dropping it down to a pH 2. So we're approaching the acidity of battery acid. Probably battery acid's 1. So you're dealing with sulfuric acid. So you're boiling it in a sulfuric acid solution for 1 hour. So what do you think is going to happen differently than the neutral detergent boiling for an hour? Is that going to be more aggressive or less aggressive? More acid. We're adding acid to the detergent. It's going to be a whole lot more aggressive about removing things and solubilizing things. So what happens here is we move hemicellulose from the insoluble to the soluble fraction. And what we're leaving behind with acid detergent fiber, ADF, or cellulose and lignin are remaining. So NDF is always going to be less. ADF is always going to be less than NDF because you're always going to have some, maybe not a lot, but you're always going to have some hemicellulose in your cell wall. The last thing we do is we soak it in 72% sulfuric acid. This is beyond battery acid. We usually do this for about 5 hours. We take that Gooch crucible, it's got the ADF in it. We pour in that sulfuric acid solution. They could probably eat through the floor. And what that solubilizes on the ADF is the cellulose. And what remains insoluble through this whole process is that lignin. So it's sort of like burning down the house, where the boards or wood represents cellulose and the lignin represents the nails. So we tend to do this in sequence. We do an NDF, wet chemistry, NDF first, ADF second, sulfuric acid, lignin last. And we divide the cell wall up. Now we have, with this system, we've got the cell contents, we've got the amount of cellulose, hemicellulose, and lignin. And we can put those into ration balancing programs and balance things out. So with the detergent system, we've got a good separation. So some people learn best with words. This can be a little confusing. Let's use a little bit more visual representation. So we take that generic plant cell and we make a grid of 25 plant cells. So each of these boxes here, we got the cell contents in green, and then the cell wall are the edges out here in black. We've got 25 cells there. So if I take that sample, run it in neutral detergent for an hour, I'm separating the cell contents, the green, from the cell wall. So if you're looking at this in the beaker when you're done, the building or the shape of the feed particles doesn't look all that different. You've taken the contents out, they pass through the filter, they are soluble, rinsed away. And what you're left with are the cell walls, the hemicellulose, cellulose, and lignin. So it's sort of like taking this building and taking everything out of each classroom and throwing it out on the lawn. We run it through an ND neutral detergent solution, neutral detergent assay. The building's still standing, but now all the rooms are empty. Anything that isn't severely nailed down, anything you can rip out, easily ends out soluble on the lawn. So we're taking out the contents, we're leaving that cell wall. If we take the NDF that's left and run it through an acid detergent for an hour, we start to take off little bits and pieces that help with the structural integrity. We might start to take out the plumbing, the electrical. In a regular house, we might be taking the molding off. We're stripping down that building to almost nothing. The building's going to be a little bit wobblier because we dug a little harder to get things out, but the building's still standing. We're taking out the hemicellulose over there, letting it rinse away. And we've got still got a, looks like a building, but it's not as strong as it was before. So we're taking out all those little tan connections. We should have a little bit more, little bit less structural integrity. If I take that acid detergent solution, acid detergent fiber, put it in sulfuric acid for 3 hours, 4 hours, 5 hours, we're basically setting the building on fire. And what we're going to be left with is pretty much the metal in the building. So think about nails or brackets and braces and all that stuff. And we've taken all the lumber and we've removed it, the cellulose. So we're removing that. We've got these nails, little pieces of lignin left. It's very, very small amount. If you start with like 2 grams of sample and run it through this sequence of analysis of sequential fiber. So if we're looking at that sequential fiber system, we're taking that 4-inch sample, we run a neutral detergent on it, cell contents become soluble, will remain NDF residue. You take that NDF, you run an acid detergent on it, you pull out the hemicellulose, you're left with acid detergent fiber. So if I run that 72% sulfuric acid on that ADF, what am I left with? Lignin's the only thing left in that beaker. Everything else has gone down the drain. We've made that cellulose soluble. Another way to look at it, as we go through, we've got the carbohydrates available. You have soluble carbohydrates, the cell wall contents readily available to the animal, the sugars and starches. So if we're thinking about the rumen digestibility here, this we'd assume is close to 100%. It's all going to disappear certainly before it gets to the back end of the cow. It's all going to be digested, all absorbed. It's fully available to the animal. If we go down all the way over here on the insoluble stuff, we're left with lignin. Lignin is indigestible. There is no biological use for a cow inside her body. She can't burn it, Some of it will be solubilized and absorbed through the gut, but it goes right out the kidney. So there's no energy value associated with the lignin. There is no potential to build with that. That's only a plant molecule. Mammals don't know what to do with it. In between, we've got our cell content or cell wall that is potentially digestible. Pectins are more digestible than hemicellulose. Hemicellulose is more digestible than cellulose. So when we think about the cell wall in total in our cows, usually about 50% of the cell wall that goes in gets digested. If things are bad, we don't get that high. We might only get 40% or 30% in the case of acidosis. If we've got a real good forage program, we might push 65 or 60% digestible. So 100% on the cell contents and something in the middle of 100% for our cell contents. The more we can extract from that NDF, better our animals do. So when we're thinking about our neutral detergent fractions, we now have fractions that have biological meaning. You don't know the old systems where they didn't, but now these systems do. Neutral detergent fiber, NDF, is what we use to balance rations with. And what we're trying to think about is about the filling effect of an individual feed. A cow can only eat so much NDF. You're looking at about 1%, 1.1% of body weight. That's all she can fit in there. So remember, NDF was, the building was still standing. So it's going to take up space, that feed, even if she digests all the contents, that building, that cell wall is going to take up space. So the more NDF we put in the diet, the more filling. Those of you interested in sale, our goal is to get as much NDF into those animals as we can to stretch out their rumens to maximum capacity. So thinking about that filling effect, you've still got the building, put that building in there, it's going to take up space. Acid detergent fiber and lignin are used to calculate digestibility. How much energy is in a particular feed? As ADF goes up, as lignin goes up, we lose digestibility of that feed. Remember what we had to do to get to ADF. Remember what we had to do to get to lignin. We're throwing large amounts of acid at it to release those chemical substances, those feed fractions. They are not as readily digestible as the other ones. So the more ADF we have, and we have to, most of the energy values for feeds are calculated based on the NDF number. So if you want an energy value, they have to run an ADF. So they can insert that into equation. Depending on which animal you are, or what stage of growth, there are different equations that you will use. So the cell contents readily available. The more of that we have, the more digestible the feed is. The carbohydrates in the cell wall, the more of that is present, the less digestible it is, particularly to us, to pigs, to chickens. Our cows can work at it and release some of it, but they're certainly not going to release all of it. You're looking at 50% is a good rule of thumb. So if this is so hard to access, so hard to extract stuff from it, why would a cow want to try to make its living off of cell wall or NDF? Cows require NDF to stay alive and healthy. They're designed for that. Why would a cow want to do that? or a deer or a moose, antelope, buffalo, bison. Why would they want to make their living off of NDF? There's lots of it around, right? It's easy to get. So we don't have to chase it. It's sitting there. As long as we can walk, we can get NDF. Well, in this part of the world, up north, it's a little tougher. So there's certain times of the year where there's not a lot of NDF sticking out of the snow. So we'll stop there today. I've got a quiz for you. Take a try at. See what your learning is. With our quizzes, I will drop half of them. So you're only going to keep your top ones, unless you want me to drop the top ones to make it difficult. But the idea behind the quizzes is I start to ask questions that you'll see on the test. It's your opportunity to see what I'm thinking, see what I think is important, and get ready for the test. So, any questions before I pass this out? So, if you show up to class, take it reasonably seriously. Quizzes are 10% of your final grade. Almost everybody in class that does those two things gets the full 10%, at least 9.5. So. So when you're done with the quiz, bring it up front, and you're free to go.